Hi, this is Steve Voldman, and I'm giving a talk today on ESD failure mechanisms and some design solutions. So we're going to go and talk about ESD and EOS. We're going to talk about chip level designs and component level design and testing. We're going to talk a little bit about failure mechanisms. In ESD phenomena, most of the models are the human body model, charge device model, machine model, and there's growing interest in charge board model, cable discharge, and another one called human metal model. Today, human body model and charge device model are standards that are used for qualification. The others are still in progress. Here's an example of an ESD failure from a human body model. You can see from the arrow that where the arrow is, there's a opening in the metal line. This is what a typical human body model failure will look like. And you can see that it's an aluminum interconnect and that there's like cotton balls coming out of the other side. Here is an example of an atomic force microscope of an ESD diode failure. You're looking at a PN diode using an atomic force microscope that went under the shell of transisolation, you could see the molten silicon underneath. Here's an example of what an off-chip driver failure looks like in a stacked device. You can see that the pattern goes from the top transistor to the bottom transistor. You can see the contact holes, then it goes under the gate, and then in the middle section. So this is a typical example of a atomic force microscope mapping of off-chip driver failure. Here's an example of a charge device model failure. Charge device model fails are typically gate dielectric failures and usually are small. There are also many failures in buses and power buses as well. Here's an example of a machine model failure. You can see in the middle of the plot, that's tungsten. The metallization is tungsten, and you could see that the tungsten was molten and went into the device. The melting temperature of tungsten is 3,400 degrees C. So you can see that that region is very hot. And this first time I saw a tungsten failure was at a 58 nanometer technology node. Failures are typically metal, interconnects, or dielectrics. Metal failures can look like this, where you're looking at a stacked via where the failure goes right through all the stacked vias. Here's again the picture of the tungsten failure from machine model. Here's an example of the critical current as a function of pulse width for a copper and aluminum interconnect. Aluminum, the melting temperature is 660 degrees Fahrenheit, and the copper wire is 1,200. As a result, you can see that the robustness of the copper wire is about 2x the aluminum wire. And actually, this plays out in the failure of chips. You will actually see a big increase comparing a copper versus aluminum-based design. Here's an example of the tungsten failure again, and you can see the thing in the middle, the triangular thing is the shell transisolation. You can see that the tungsten actually goes into the silicon and starts to try to work its way around the shell transisolation. MOSFETs also fail. MOSFETs, here's an example of breakdown of the black circles as the breakdown voltage, and the squares, the white squares, as the first trigger voltage. As you scale technologies, things get the breakdown voltage of the junction starts approaching the trigger voltage of the transistor. And the results keep going down as we scale. There's many dielectric models, but just to give you a taste, here's one of the more well-known ones by Chen-Ming Hu, and it's called Fong and Hu. You can see that the time to breakdown is a function of two constants and inversely proportional to the oxide field. Here's an example of plotting that on the line, and you can see the trend fits that physical model. Another model that's popular was by Bonnie Weir. These are breakdown voltage models, and it's comparing breakdown voltage for area, breakdown voltage for one area versus another area. There's also a reference to a publication down there. Another model, which is a more recent model, is by Ernest Wu. Ernest Wu was from IBM Burlington, Vermont. And in his model, he takes into account both voltage and temperature. And basically, some of the early models do not take into account temperature. They just are associated with voltage. There's different forms of electrical overstress. Electrical overstress is a broad term, but there's also different phenomena that we're concerned with. Electromagnetic compatibility, electromagnetic interference, Latchup, ESD, and EOS. Now, Latchup and ESD are a form of electrical overstress. Electrical overstress is a broad spectrum. It can be associated with electrical over voltage, electrical over current. And then there's ESD, EMI, and EMC. EOS phenomena can occur in devices, components, or systems, printed circuit boards, components, wire bonds, and silicon. Typically, for electrostatic discharge, you don't see failure in the printed circuit board or the physical package or wire bonds. What is the cost of electrical overstress? Manufacturing yield loss, production, field returns, system failures, and customer satisfaction. Electrical overstress that occurs in products can impact all kinds of equipment, any kind of electronic equipment or systems, and everything from airplanes to automobiles. Product field returns also impact the yield of an application. There's retest recovery, and there's thermal overstress as well as latchup. If we were to put this on a safe operating area chart, you would see that there's a current, a region which is the safe operating area, which is a certain current and voltage characteristic. On the vertical axis, there's a current limit where basically the failure will occur. On the x-axis is a voltage limit. And then on the corner, there's basically second breakdown and thermal limitations. So this is how you can determine whether you're in a safe zone for applications or not. There's also a transient safe operating area, which is basically takes into account the peak, and it's a function of time. Let's see. What's some of the origins of electrical overstress? Voltage, SOA, voltage rating violation, power rating, or current, because as we just showed a couple minutes ago. But EOS can also occur due to product application mismatch, product technology mismatch, board inductance, and board resistance and floating nodes. EOS can be from productions, lightning, power, relays, coils, actuators, any kind of electronic equipment. Here's an example of an electrical overstress wire bond failure. Here's an example of EOS on a chip, and you can see the ESD typically doesn't take out that many pins. So the fact that it's a wide area and the discoloration is because there's mechanical stress in the insulators. Here's an example of an EOS from a packaging failure. This can be thermal overstress, latchup, or another form of electrical overstress. Bulging or ablation in the package is usually also the same. Could be latchup, could be EOS, could be thermal overstress. All these things are different forms of how they're initiated. In this kind of event, actually the package can physically explode and separate from the device. You can tell that this is EOS by the size of the large area. Here's an example of plasma arcing, where basically an electrical arc occurred and went all the way through the physical via structures. What are some of the physical models of this? If you would look at equations, there's something called the Tasca model, which is a spherical source assumption. The Tasca model is basically the solution of the thermal diffusion equation in terms of the power to failure versus the other parameters. Another person at the same time frame also produced a model which was one-dimensional. It was Donald Wunsch and Bell. It's known as the Wunsch-Bell Model. This is an example of the equation associated with Dante Tasca's model. And you can see in the parameters the power to failure. It's inversely proportional. There's three terms. There's a volumetric term, a surface area term, and a time-independent term. And this leads to three physical kinks in the power to failure over area versus log pulse width. And you can think of this as a universal curve sweeping all the different pulse widths on the device. Wunsch-Bell also produced the same physical curve representing the device. But now there's more interest in electrical overstress. The region of the slower time constant is also now thought of as the EOS regime, and there's a slow EOS and fast EOS. And notice that it's penetrating into the 1 over the inverse time region. A three-dimensional model, which has been increasing in popularity, was introduced by Dwyer, Franklin, and Campbell out of England. And what you can see is in that EOS regime, there's a term which is inversely proportional to the log of time. Let's go talk about testing briefly. What does the human body model look like? The human body model looks like it's got a 17 to 22 nanosecond rise time and like about 150 nanosecond decay. The circuit model is basically a capacitor and a resistor. And actually, this is an example of the resistor capacitor network from a source. Here's an example of an HBM wafer level tester. This is an example of a charge device model tester. There's also something known as transmission line pulse testing. There are 4 configurations. I'm just going to show you 2. One is known as the current TLP current source configuration. The other one is time domain and reflection transmission. From this characteristic, we can determine an IV profile showing the kinks in the device of the avalanche breakdown, the reverse resistance regime, the linear regime, and breakdown. EOS and ESD have different pulse waveforms. EOS can be a very long pulse, while for ESD, they're very well-defined standards for human body model, machine model, and another test called the IEC 61000-4-2. There is a voltage axis where there's an ESD voltage window, and then there's a window where electrical overstress is above ABS max. What does cable discharge waveforms look like? It looks like basically a square pulse. And what you're looking at is the square pulse phenomenon. Here's an example of a IEC waveform. Then there's a human metal model, which uses the same configuration, but it's a gun, and only certain test points are used. The human metal model is performed on the chip itself, where the IEC test is typically done on a system. Here's an example of a surge test of another IEC test called 61000-4-5, an open circuit and short circuit. Another thing that's of growing interest is EOS-induced EMI system failure. Here's an example of a scanning system that basically introduces a pulse into a chip to see the response. Here's one of the early versions of a large scanning system by Amber Precision. Here's a smaller version that came out in the future. And this is what the characteristic looks like. Basically, what the armature produces a small electromagnetic pulse, and the image you're seeing is the region of a chip that is impacted by the pulse waveform. There's another methodology very similar developed by Jeff Donahue, which instead of sweeping the pulse over the top of the chip, you actually inject the pulse into the pin of interest and look at the response. And then the current is reconstructed from the E and H field emissions from the test. So there's been significant advancements in the idea of testing systems. Here's an example of 3 different versions looking at the pulse waveforms from this conversion reconstruction methodology. So what are some kind of on-chip solutions? Well, a well-known one is the dual diode network. A second common one is the grounded gate NFET, which is sometimes called a GGNMOS. Silicon-controlled rectifiers are also used as a way to add ESD protection. And then within the power grid are placed RC-triggered MOSFET clamps to discharge current between VDD and ground. In EOS, there's also voltage suppression and current limitations. One way to limit the current is to put an element in series with the incoming nodes on an input and an output. Here's an example of a voltage limiting device where basically it's going to ground. Schottkys are used, Zener diodes are used, metal oxide varistors, and metal oxide varistors are also used to protect EOS systems. And there's other methodologies where some of the solutions are actually built into the circuitry using current limits, voltage limits, and thermal shutdown. There's receiver circuit protection for human body model and charge device model. Here's an example of a circuit where you actually modify the circuit to provide protection for this circuitry. And here's an example of the modified keeper network to increase the ESD protection level. And here's the full circuit with the charge device MOSFET included in the circuit. Schmitt triggers also have feedback loops which cause failures. A very simple solution is the addition of resistors in the feedback loop. Differential circuits need to have double diode networks on both of the inputs. But also, one of the failure mechanisms, which is quite common, is a pin-to-pin failure in differential circuits. So we need to add pin-to-pin ESD protection networks. So in summary, the ESD and EOS failure mechanisms still occur in circuits as technology scales. And there are both system-level failures, component-level failures, and circuit failures. And all these things impact reliability, and it is a common problem today and will continue to be in the future.